we are given this system, we need to check the type of the populations and the interaction. So you see that the coefficient of x and y here are both negative. So two populations x and y, they are both naturally decreasing. And you see when they have interaction x and y, so the coefficient here is 3 and 1, so they are both positive. So actually they help each other, lining, and they help each other. So in this case we have population in cooperation. So they help each other. Second one, they give us the critical points 4, 2 and 0, 0. We will look at the behavior near these two critical points. So let's compute the Jacobian matrix. Call this F and G. So we have Fx, Fy, Gx, Gy, and the Jacobian matrix is Fx will be 3 times y minus 6, Fy 3 times x, y and x minus 4. Now we look at the critical points 0, 0. Jacobian matrix at 0, 0, minus 6, 0, 0, minus 4. So we have two eigenvalues. In this case, two negative eigenvalues. Lambda 1 minus 6, lambda 2 minus 4. So both negative. So we could have a 0, 0 is an asymptotically stable node. So this is a nodal sink. So that is the type is stability is asymptotically stable. Second one we have 4, 2. So if we can just do it now, find the eigenvectors. So lambda 1 equal to minus 6. Correspond to that we have v1 1, 0. This is 1, 0. This is a diagonal matrix. So in choose this one to be 1, 0. The second one 0, 1. Lambda 2 minus 4. We want to sketch that. We have 1, 0 and 0, 1, and both are sync. So both reactions state is going with. And now we have 1, 0 correspond to lambda 1 equal to minus 6, lambda 2 minus 4, v1, v2. So when we have the general solution, C1 v1 is lambda 1t, C2 v2 is lambda 2t. So when t is tend to infinity, this one decays faster. So it's follow this one dominate. So it's going to look like this. So here's a picture. Now we look at the second critical points for 2. Jacobian matrix is this one. At 4, 2. 3 times 2 minus 6, 3 times 4, 2, 4 minus 4, 0, 12, 2, 0, minus lambda, 12, 2 minus lambda. This is lambda square minus 24 equals 0. Lambda equal plus minus root 24. So one positive, one negative, we have a saddle point. It's a saddle point. This is not a special case, so it's a saddle point of the almost linear system. So yeah, this is unstable. We know that we have a sink in the origin 0, 0. So we would expect to have one direction go into the origin here. So because it's a saddle, so the in, the other one go out. And then we should have something like that. So from infinity, this one should go in. Maybe like this. Maybe we would expect something like this. So So here we just vibe check it without computing explicitly. And so see something like this. So the long-term behavior. So the other side just go here, go off infinity. So there is a separatrix here. If it's below the separatrix, so let me highlight this. Separatrix is this one. So if we are in the region below it, so expect that both of the population will die, will be extinction. No matter where it starts, no matter the initial condition, if we start below the separatrix, there's the red one, separatrix, then it will be extinction. If we start from somewhere here, above the separatrix, then they will grow unbounded. So note the long-term behavior. Depends on the initial condition. So if the initial condition is below the separatrix, both population will be extinction, and above separators in growth and bound.